Oh, hello, guys. I see only 16 students. That means I do not frighten you enough. That's too bad. The most frightening people are those that are unassuming. So what have we been doing during the past lecture? We have tried to understand a very important property of expected value. And in particular, we know that expected value is additive. Yes, so the expected value of x plus y is the expected value of x plus the expected value of y. That's a very fundamental result. And we can arrive at it very simply by just grouping based on the sample space, right? So when we are doing expected value, what you should imagine is you generate an idealized table. And in this table, what you have, you collapse all the outcomes from the sample space that are the same and just count how many times they occur and divide by the total number of trials, which will then produce probabilities. So then you have element S corresponding to the probability. Yes, and then we have the score X of S. And to figure out expected value is just to average those scores. Yes. Now, what it ends up happening is the same as multiplying the score X of S times the probability that S happens. And if you use that definition, or you use that version of calculating the expected value, you should be able to see this pattern. I hope you do. Yes, it's very, very useful. So with the expected value of x plus y, I can construct the variable z, group whenever x plus y are the same score, and then collapse the probabilities corresponding to it. That will be the one calculation. But it's not the calculation that easily shows that expected value is additive. Good. And we solved a bunch of examples. And then in particular, here is one example where it's pretty important. We try to calculate the expected value of performing n independent experiments, in each experiment having probability p. Yes, we can solve that intuitively and see that it's equal to n times p, but we can also have a very easy calculation for it. And that calculation will be simply as follows. We can define x. X is the number of successful outcomes among n experiments as a combination of x1 plus x2 plus x3 all the way to xn, when each of them is called an indicator random variable. In other words, what it does, it looks at the full sequence and ignores everything other than, let's say, the kth entry in that sequence. So the sequence of successes and failures is a sequence of zeros and ones. Yes, and it looks into the kth position of that string of numbers, and it says, oh, it's either 1 or 0. Yes, so it will give you that index, either 1 or 0. And then the expected value of all of them is the expected value of each of them individually, because it doesn't matter dependent or not, that's always true. Yes, and then what's the expected value of x1, for instance? x1 means that it's 1 times the probability that the string begins with a 1 and 0 otherwise. Now the string begins with a 1 with probability p, because all the others, p minus p, p minus p, they don't affect it. I hope you can see that, right? So if the first string is 1, the rest can be anything they like, so it's just the probability p. And similarly for every single other xk. So that's the same thing as n multiplied by 1 times p plus 0 times 1 minus p, which is n times p. I hope you understood my analysis here. Yes, guys? Like throwing a coin, I mean, you just look at the first entry in this string, and you can see that all possible strings are just determined by the first entry, either p, probability p that we have 1, or 1 minus p that we don't have. Okay, and then we solved this question. That's where I believe we were done. And we tried to illustrate with this question that if you calculate expected value by the definition given in the textbook, you might arrive at this calculation, which is pretty difficult. You can still carry it through, but it's very difficult. And there will be many other calculations which you will not be able to carry through. Yes, but if you solve this question using the expected value, sum of expected value is the expected value of the sum, then you can very quickly, with almost one line, get to the expected value of X, where X was, if you remember the question, the number of men serving in this committee of size 10. So we had 10 women, 10 men, and we want to know what's the expected number of men on the committee. By symmetry, you should expect that there would be half, 5, on average 5, if there is no bias in selecting. Yes, so that's why I selected this question. So it's very easy to see it's 5, and it's easy to see that the calculation works well. So the way we do it quickly is we say, well, the number of men is the summation of which men are present, right? So we have 10 possible men. So we have xk. It's an indicator variable that searches for the sample and looks whether or not the sample has that men. Yes, so and then we add up. So if person k, if man k is in the sample, I add 1. If not, I add 0. And the strings of sums of 1s and 0s will give you the total number of men. Agreed? Now, what's the expected value of all the men? It's then the sum of expected value of x1 plus expected value of x2 and onwards. Now, I hope you can see that by symmetry, they're all the same expected value. There is symmetry here, right? Men 1, the average time men 1 will be the same as the average time men 2 will be there. So we do use symmetry. Now, what's the expected value of x1? Well, you see, I can right away say 10 over 20. How do I know that? Well, you can either calculate all the samples of size 10 where person number 1 is there. And that would be how many? That would be 19, choose 9, divided by 20, choose 10. Yes? The other thing you can do, which is faster to calculate this number, it's the same number, is just to remember the pass dispenser analogy, right? So you can imagine the pass dispenser, it has 10 slots in front, and also the candies you will select. And then it has other 10 slots in the back. Altogether, it has 20 slots. Now, the candy, this man number 1, is equally likely to be anywhere within the pass dispenser. Yes, in any of the 20 positions, as long as this candy is in the first 10 positions, it's selected. That's why it's 10 over 20. You see that I use that very frequently. It's a very useful calculation. It simplifies lots of things. So 19 choose 9 divided by 20 choose 10 is 10 over 20. You can do that by calculation, but you can just reason this way very fast. Good. Now here, let's try to understand how to compute the expected number of matches in the matching problem. Do you remember the matching problem? So you have this place, this club where gentlemen are meeting, and they each have hats that they bring to the club, and then randomly each gentleman wears a hat on their way out. What's the number of times we will have the person leaving with the same hat as what they came with, right? So we have hat 1 and gentleman 1, hat 2, gentleman 2. How many matches do we have on average? So we can do that. Remember that we calculated the probability that there will be no matches to be e to the power of -1, if you remember, right? When the number of gentlemen is large, the probability that nobody leaves with their own hat is e to the -1. And the probability that exactly k gentlemen leave with their own hats is e to the power of -1 divided by k factorial. Right? So this, I mean, I'm just reciting. You can just go back to the notes, or in office hours, we can discuss again how to calculate that. But that's the results. Now, we want to understand just on average, how many gentlemen will leave with their own hat. Right? So how do I know that? Okay, well, let's do it this way. We can define xk to be the indicator variable, and that is 1 if the kth person picked the KF hat. So if gentleman 1 picks hat number 1, then x1 is equal to 1, right? And then all we have to do is just add up x1 plus x2 plus all the way to xn, because that summation will be the number of hats that are worn by the owners. Good. And this is not independent random variables. Do you agree? What gentleman 1 does will affect what gentleman 2 does, because I mean, maybe gentleman 1 picks his hat, so gentleman 2 no longer has the ability of picking his own hat. But it doesn't matter for expected value. That's the amazing thing, guys. Expected value of the sum is always the sum of expected values, whether the random variables are dependent or not. So we know that this is the expected value of x1 plus expected value of x2 and onwards. So, and I see symmetry. Now, why do I see symmetry, guys? If I have tunnel vision and I focus on just one gentleman, right, then the probability that he picks his own hat is good. There's no preference. You agree? It's done randomly. So if I just focus on gentleman 1, he picks his own hat with frequency 1 out of n. Do you see that? Right? In other words, I do the trials. I mean, there is no nature is completely indifferent. There is no prevalence of who picks his own hat or not. There is no prevalence to the hat the gentleman picks. So if I just have tunnel vision and I just focus on gentleman 1, I see that in all the strings, and every time I run the simulation, gentleman 1 picks his own hat about 1 out of n trials. And n is the number of gentlemen. And the same is true for gentlemen 2, 3, and onwards. That means that the expected value for each of them is the same. So what do we get? We get expected value of xk is 1 over n, and we multiply it by n, and we see the answer is 1. So that means on average, guys, no matter how many people are playing the game, on average, only one person will pick the hat, his own hat. Interesting, right? On average, only one person picks his own hat. That's very, very important, guys. If you are able to calculate the average, it will also allow you to frequently estimate probabilities, not always calculate them exactly, but give a very good estimate. Are you so far following me, guys, right? It's such a tremendously important thing that if you understood nothing from this class, I hope that's one of those things that you actually somehow get. All right. Let's try this example. And maybe you will calculate the expected value for me. Can you do that? We have urn with n balls, and k of which are blue, n minus k are red. We take a sample m, which is less than or equal to n. What's the expected number of blue balls in the sample? Does it make sense, guys? We have some large amount n. We take a smaller sample. We know how many blue we have, how many red we have. How many, on average, blue balls do we have in the sample? Well, good for you, Nicholas. Don't worry about it. It's pretty funny that you mentioned, but yeah, I would just not come to classes when I went to school. Okay, interesting. Let me think for a second, guys. Okay, Ryder. Okay, guys. So let's think of it. So perhaps we can imagine taking the balls out sequentially. You agree? That's the easier thing because then we can simply label which comes first, which comes later. So if we take them sequentially, we can say x sub j is the jth ball that is removed, and I will label it would contribute 1 if the ball is blue, and otherwise contribute 0. Yes. Now the expected value is the sum of the expected values. You can see the variables are not at all independent. If I withdraw first ball is blue, that I withdraw the next one is less likely to be blue. But when I take the expected value, I want to know, okay, what's the expected value of xj, the jth ball? I just then look at the average, and I look only at the average is of inputs that are of length m, right? So I have zeros and ones, string of zeros and ones of length m, and xj means look at the jth string in each of them. And then how often is the jth string going to be equal to 1? Well, in the jth place, every ball labeled 1 through n is equally likely to occur. Exactly k of them are blue. Yes. So the expected value of xj is the probability times 1 plus 0 times the probability doesn't happen. It's not a blue ball. So it's just k over n. You agree? K over n is the expected value of the jf of xj, and the expected value for the total is just the sum. So it's m multiplied by k divided by n. You follow? You see what I do, guys? Yes. So expected value allows me to break the string and focus on only one input and ignore, in some sense, ignore the others. They are not non-existent. You know what I'm imagining? I'm imagining a string. Each experiment consists of a sample of size m. So there is a string of ones and zeros of length m. Yes. And what I do when I calculate expected value, I focus on the first coordinate of the string, second coordinate of the string separately, ignoring the others. I look at it and I group by when is first 1 and when first element of the string is 0. So all I do whenever I calculate expected values, I sort my tables, I sort my sample spaces. Yes. So here, when I calculate expected value of x1, I sort my S's, my table of samples based on first number being 1 or first number being 0. And I see that the proportion of in my table k over n begin with a 1. Yes, that's the probability. You see, and I calculate the expected value of x1 based on that. And then I do the calculation for x2 and do the sorting for the second coordinate. Good. You follow, guys? You see, so I hope you have the same type of vision that I do, right? But not when you're driving, because if you do that when you're driving, you might crash. It happened to me. Okay. Now the next question. Let's see if we can solve this one together. We have an urn, and it has one red and one blue ball initially, and then we take a ball out, observe it, and replace with additional ball of the same color. You understand? So if I pulled out a red ball, I then the next time I will look into my urn, I have 2 red and 1 blue. Yes. Now I want you to tell me what is the probability that the first ball removed, that is blue, is on the kth trial. Make sense? So what's the probability I remove blue ball on the first trial for the very first time, or on the second trial, on the third trial, right? So calculate probability that x equals to k, please. One have to start with, but in general, I mean, this is supposed to tell you the probability if your first withdrawal of blue is on the kth trial, where k could be first, second, third, fourth, and onwards, right? Yes, first is obviously P of X equal to 1, it's obviously 1/2. It's either blue or yes. Careful, careful, guys. For the first time, you remove, okay, so you're saying 1 over n plus 1. Somebody said factorial, or maybe it's an exclamation mark, first a question mark, then an exclamation mark. We'll see. All I'm asking is not which ball, but whether it's blue or red on the cave trial. I didn't say you're wrong. I'm just mentioning what I'm asking, right? To be precise. Don't neglect your Kafka protocols. All right, let's try to solve the first together, guys. So red is on first k minus 1 trials. Yes, red on first k minus 1 trials, and blue on the kth trial. What does it mean? It means first we don't remove blue all the way until this. The k minus 1 removal, it's still red. So red in the first k minus 1 removals, blue is the last removal. So first is 1/2, next is 2/3. You see, I mean, I can use conditions, right? Conditional. So first 1/2. Given I did not remove blue, the probability I remove red is 2/3, right? And then 3/4 all the way to k minus 1 over k. And the final one is blue out of k plus 1 available balls. So it's 1 over k plus 1. We have only one blue, right? And then what do we get? You can see numerator is k minus 1 factorial. Denominator is k plus 1 factorial. You agree? I mean, it's missing a 1, but it doesn't matter. It's k plus 1 factorial. And so when I simplify it, the answer is 1 over k plus 1. You agree with me? Good. Guys, always be very methodical about it, either conditional probability or Kafka protocol, whichever you find useful in the situation, right? And then you will not make a mistake. So it's 1 over k plus 1. Now, what do you think is the expected value of x? So you see the probability that I will get a blue ball on the kth trial is 1 over k plus 1. What's the expected number of what's the expected moment when I remove the blue ball? not the probability, expected number of withdrawals. And so yes, you might imagine that if I continue withdrawing balls, eventually I will take out a blue ball, right? But the question is on average, how many withdrawals do I perform before I take out a blue ball? Don't be shy. What do you think? Is it 1, 2, 3, 4? How many of you think the answer is 1? Just write 1. In other words, on average, I will remove the blue ball in one trial. Okay. Right, on the second trial. Okay, that's why you were hesitant, right? You don't like infinity. Let's look at this calculation, guys. So in this case, the easiest way to figure out the expected value is just to multiply the probability by the score, right? So here it's grouped. What's the probability that x is equal to k? It's 1 over k plus 1k. And if it's that probability, the number of withdrawals was k. Yes. So what do we have when we cross out k's? We get summation of harmonic series, which diverges. So on average, it will take you infinitely long to withdraw a blue ball. Isn't it interesting? Does it bother you guys? I mean, the probability that you withdraw it on the first trial is 1/2. So it's already 1/2 as likely that you will finish it once you do it once. But apparently, on average, it will take you forever to get to the blue ball. You see, guys, average is this. You see, what's average, right? Average just means there are some cases, there are some situations in which you would really mess up, right? And you will continue messing up. You see, guys, it's very likely that, let's say, you don't withdraw it for the first time, then maybe it's already more likely you won't withdraw it for the second time. It's even more likely you won't withdraw it for the third time, right? As soon as you withdraw a red ball, it makes it more likely that you will withdraw a red ball again. And each time that happens, that just makes the sequence very long. Even if the probability were always 1/2, it's not uncommon to see very long runs. You see, guys, so people that are trying to pretend that they are random, they usually have, let's say, like 1 2 1 2 1 2. They think like this, right? But randomness does not look like it. So you have very long runs, like let's say 1 1 1 1 1 1 1 1, right? It may be 10 times, and that's if it's equally likely, right? But here, once you begin to have a run of failures, your next failure just is made more likely. You understand? So imagine you did not withdraw the ball 10 times, right? It's already more than, or it's already less than 10% likely that you will withdraw it on the next time. And with each iterate, it becomes very unlikely that you will find it. So you see, it's a sort of like, I don't know what's the analogy, right? I remember that thing from Harry Potter when you have those chalices just doubling, right? And as you're trying to reach for something, I don't remember what he was trying to reach exactly for, but you have those chalices replicating. You cannot get to the right one. You cannot reach it. Yes? Of course. It will, by symmetry, it would be infinity for the red ball too. So on average, it will take you infinitely long to withdraw anything from that urn. It's like a magical Harry Potter urn, right? Or whatever it is. I'm not sure if you're reading Harry Potter. I never did, but it used to be popular. I knew people that are very, obsessed about it, just many of them. But maybe it's already passed for you, right? It is still popular. What do I know? Popularish, right? You should read Astrid Lindgren. That's funny. I think that you have this middle-aged man that flies to visit children with a propeller on his back. That's stories that I like. So, all right. So let's look at this. Okay. I need to show you Carlson at some point. If you want to, if you want to, at the end of the class, if you're interested, I'll show you a quick. The Russians have a nice cartoon. I'm not sure if it will do anything for you, but you have this guy and he has this propeller, like a fan on his back. So anyhow, we have a fair coin is tossed 16 times. What's the average number of times the pattern head, tail, tail, head will be observed? That's a bit hard question, guys. I'll give you maybe unfairly, but only, let's say, 6 minutes to think about it. Maybe if I have time, I'll create a simulation for that chalice question or that red ball, blue ball question, so you can see what numbers appear when you try it. Well, there is a 13 factorial, Gustavo. I'm not sure why. And yeah, there is something that looks like there is right in your calculation, but somehow I cannot make it. Gustavo, it sounds like you have the right idea, but see if you can just look at the formula and maybe you need to correct something about it. Very nice, Chiara. All right. I suppose let's look at the question. How can we solve it, guys? So first of all, we can imagine running indicator random variables, right? So we have a string. The string is made out of 16 letters, each of them either H or T. Yes. And we want to read how many times we see H, T, T, H. So what we can define are variables that read the first variable that reads the first 4 strings. The next variable reads the first 4 strings after the first, or should I say, starting from position 2 all the way to position 5, it reads the strings, right? And so on and so forth. So how many variables can I define? Well, the last variable that has a chance of catching HTTH has to start at 16 minus 4 plus 1, or at position 13. You see, x1 starts in position 1 of the 16 letter string. Yes, x2 starts in position 2, and the last one has to start at position 16 minus 4 plus 1. You see, 16 minus 4 means I remove 4 of them, but I don't want to start from before removing 4, so I add 1. I hope you understand the plus 1 meaning here, guys. Yes. Yes. It's a bit, I take 16 minus 4. That's the last 4 that I can read. But that means that I overshot by 1. 16 minus 4 means I went 16, 15, 14, 13, and 12. So then I have plus 1. I go back to the 13th position. So there are in total 13 random variables. Do you agree? And each of them is 1 if the kf through k plus third toss are HTTH. Yes. So then what's the expected value of all of them is just the sum of all the 13 random variables. And then they are the same. You agree, guys? If I just look at any region with 4 strings and I just average, because of randomness, they're equally likely to be any letters H combined with H and T with equal probability. So they are going to be, it's 1 over 16, right? Because it's 1/2 times 1/2 times 1/2. Each letter in each position is either H or T, and altogether we have 1 string that I like out of 16 possible strings. You agree? Just it must be what? It must be first position has to be H, second position has to be T, next position T, and the last H. So there is only 1, but altogether there are 16 possibilities. Good. And then because there are 13 of them, it's 13 divided by 16. In general, if I have if I perform the experiment n times, it's going to be n minus 3 divided by 16. That's how many times I will see on average the string HTTH. And you see, you can see that it's selected. They can be overlapped. So for instance, the next string might begin with this H. So I can read it as HTTH. It's 2 of them because I read 4, and then from this one I read another. Yes. I hope it makes sense, guys. And then we're ready to move to the next lecture. Properties of variance. So we know that without any conditions, the expected value of the sum of variables is the sum of expected values. Is it true or not for variance? We want to know, is it true that variance of the sum is sum of variances? Yes, guys? And for that, we need to examine, to see whether or not it's true, we need to examine a broader definition. It's called covariance. And I like that word covariance because in Russian, kavarny, I'll write it maybe with English letters. I don't think it matters, but you know. So kovarny, I'm not sure how to spell it. You know, I can spell it with Russian letters. Kavarny means insidious or you know, schemy. Yes, or cruel. So covariance is then the natural thing to do with me around. So what is covariance of X and Y? The covariance of X and Y is the expected value of the product of X minus its expected value times Y minus its expected value. Do you see that if I take covariance of X with X, that is just reducing to the variance definition. Yes. So covariance just allows me to not always be stuck with comparing X with X. I can also compare X with Y. So it's more broad. That's a broader description than just variance. Yes. So what do we observe? We observe that covariance is what? When I multiply things out, I can calculate the expected value, right? So it's X times Y minus mu XY minus X mu Y and blah, 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 right? So what is that? Those are additive. I can add them. So it's the expected value of XY minus mu X expected value of Y minus mu Y expected value of X plus mu X mu Y. Now, what happens here, guys? This is mu X mu Y, mu X mu Y, and mu X mu Y. So when we simplify, what do we get? We get simply the expected value of XY minus the expected value of X times the expected value of Y. Do you see that? Which, if it were variance, it would be expected value of X squared minus the square of expected value. But here you have this expected value of product of random variables times the product or minus the product of expected values. I'm sorry. Yeah. So some simple properties to consider. Naturally, covariance of X and Y is the same as covariance of Y and X. You agree? Just rearranging terms here, it's multiplication. It doesn't change anything. Right? If I place Y first and X later, it will just write the same formula, but reshuffle the terms. B, as I mentioned, covariance of X with itself is just the variance of X. It has this it's called bilinear, if you remember. I mean, you see the reason you don't use that language is when you say linear function or linear map, you have a vector space in mind. But here we just have a sample space in mind. But aside from that, you can see that covariance, if expected value is analogous to a linear map, you see it's additive and you can move scalars out. You all know what linear maps are, correct? You took linear algebra. Yes? And that it was, did you like the subject? No? That's because you probably...
I took it over the summer, so it was very fast.
Mm-hmm.
But I'm sure with more time, I would have enjoyed it more.
Yes, it's not all, it depends, of course, what topics, but it's pretty, it depends also what book you use.
Right.
Yeah, but if you want, I can recommend some books for that as well. But yes, like let's say if you look at quantum mechanics, I, by the way, can show you a simple book more or less about it. So it's a combination of what? It's a combination of linear algebra with probability with analysis. That's the mathematics of it, at least, right? And it's not enough to understand it because it's weird. Yes, but anyhow, so I'm getting distracted by all this interesting side notes. But you see, what is covariance? The analogy is that it's linear in each of its variables. So if I fix one variable, let's say I fix y, I see that I can factor a scalar out, and I see that the covariance is additive. I'm going to prove it. You see, so that means that's known as bilinear map, at least when you have vector spaces in mind. You don't call it this way in this context because we don't have a vector space in mind. Yes. But it behaves like a linear map aside from that. So anyhow, so A is obvious, B is obvious, C pretty obvious because look at it. What's covariance of AX time and with Y? It's the expected value of AX with Y minus expected value AX, expected value of Y. So here I can factor out A by the additivity by the scalar multiplicativity of expected value, and here I do the same. So you can see that I can move scalars out. Similarly for addition, look at it. It's just an obvious multiplication, you agree? It's just expected value of X plus Y, X1 plus X2 times Y minus the corresponding expected values. And here I just readjust them. I just multiply Y through X1 and X2 and separate the expected values. And here I do the same. And once I rearrange everything, I get covariance X1Y plus covariance X2Y, which you can obviously verify and should. Yes?
I have a general question.
Go ahead.
So X and Y can be any two like numbers. They don't have to be like, I'm asking, does Y have to be the response variable to X? Like, does
No,
this
I
have
mean,
to be
well,
or is it a
first of
number?
all, remember the context. You have to really, you
Right.
see, you cannot just combine our arbitrary variable X and Y. They have to be operating on the same sample space. Otherwise,
Okay.
it's meaningless.
Right.
So you must have a very clear image of the sample space that you have. And X is just one way of relabeling the sample space, and Y is another way of relabeling the sample space. So you have like, let's say, red label and blue label, right? So same outcomes, but you have red label and blue label on them, right? And X times Y is like a product of those labels.
Okay, got it.
Yes. Good. Okay, guys. So far, you follow what's happening, guys, right? We just made a more general definition that captures as a particular example what is variance. Yes, and then we observe just some properties, some functional properties of this operation, and we see that it behaves so B and C, better said C and D, they make it kind of like a linear map in each fixed coordinate. Yes. And so what do we see about variance? So what is variance of the summation xk, right? The variance is this thing. It's just this, let me, before I read it out, it looks scary. Let me explain, for instance, what's variance of x plus y? Let's begin simple, right? So I'm claiming it's the same thing as variance of x plus variance of y plus 2 covariance xy. That's what I'm claiming it to be. And I'm claiming that variance of x plus y plus z will be variance x, plus variance y plus variance z, plus 2 covariance xy plus 2 covariance xz plus 2 covariance yz, which, as you can see, is not always the same as variance x, variance plus variance y plus variance z. It will be so only if covariances are 0. That's why you remember covariance is this insidious, it's this bloodthirsty thing that is not always 0, right? Now, let's try to understand this corollary, guys. You see what happens, right? So I have a summation in each coordinate, and when I expand it, it's like multiplication. Do you see what happens? Covariance between this expression and that expression is very simple, similar to multiplication. Do you agree? What do you do in multiplication? Let me maybe illustrate it for you. Here is multiplication, right? So if I have x plus y multiplied by x plus y, what do? You have a combination. So you combine this x with this x. You combine this x with this y. You combine this y with this x, and you combine this y with this y. Yes? That's what you do with a product. Great. Now, what happens if you calculate covariance of x plus y with x plus y? Exactly the same thing. This covariance, it behaves as if it were multiplication. You agree? Why? Because I can expand it. And I can write covariance x plus y plus covariance y x plus y. Yes? And then each of them I can expand further, because again, we can shift second coordinate and first coordinate, they can be shifted, it's the same. And I can write it as covariance x plus covariance xy. And the second part I can write as covariance xx plus covariance xy, or sorry, second is covariance yx, right? It should be y. And this should be also y. Are you in agreement with me, guys? And do you see what happened really, right? What really happened from a combinatorial standpoint, I simply combined each element from first coordinate, from first part or first coordinate, I'm not sure what to call it, with each of the second. Right? We have here is the x and x. This is this x with this x. This is this x with this y. This is this y with this x, and this y with this y. So just like with multiplication, you just combine them. Instead of writing multiplication, you write the word covariance in between. Yes, that's what it's very easy. Once you understand that you can break it in one coordinate, you can understand that that must be exactly what happens. And because a bunch of them are the same, so for instance, this is the same as that, right? I can simply replace it by two covariants xy. Good? No one is confused so far, correct? I'll try to do my job better. So this is the general situation. That's what this is writing, right, guys? This means just add everything up, right? That's the corollary, just add everything up. And then I decide, well, I can group it by variance, right? So there is only one instance where the x from the left side of the parenthesis means the x of the right side of the parenthesis. Whereas there is when it's heterogeneous, so there is x meeting with y and y meeting with x. And that's what this is capturing, right? That's the summation for, I just grouped it by first coordinate and grouped it against the second coordinate. But you could just replace this by writing it twice times a combination of a heterogeneous combination of left part of the parenthesis with the right part of the parenthesis. Yes. Now, how many terms are in this summation, guys? Just to check, comprehension check, how many terms in the summation? It's important, you will need it. Right, do you agree that there is, if I have, let me just make it. Let's do it this way. So I have covariance of x plus y plus z. With x plus y plus z, right? Now, you agree that I have only one combination with x meeting x. I call it homogeneous, homogeneous connection, whatever we call it, right? So I have covariance of x and x, which I can write as variance x, yes? Plus I have only one connection with y, where y meets y. And similar for z, right? Plus, what happens next? Next, we have how many connections? So how long is the this summation? How many terms do we have here? 6, 3 factorial. So how to calculate in general? So there is 3 of them, right, guys? So I can say, okay, this is 3 choose 2. 3 choose 2 are the variables, right? I'm not sure if it's left or right. You agree? 3 choose 2 means I have 2 numbers out of 3. It's maybe x and z that are meeting, or y and z that are meeting. There are 3 choose 2 of them, right? And then I can multiply this by 2, because either the smaller value is first followed by bigger value or vice versa. It's either x z or zx. Do you follow? 3 choose 2 just tells me which of them met. And if, of course, there might be different variables. Maybe this is x1, y1, z1, and this is x2, y2, z2. But in general, I mean, when we are doing it, they are going to be the same. right? So if they're the same, I can just shorten it and I can make it 3 choose 2 and I multiply everything by 2. Because it doesn't matter if it's xz or zx, I just write it xz and multiply the full sum by 2. Good? Very nice. So we understand, yes? That's what this 2. So it's 2 times 3 because 3 choose 2 is 3, and I multiply everything by 2 in this case. All right, so you can see that unless all of those terms are 0 or, or cancel out to 0 somehow, then we don't have that variance of the sum is the sum of the variance. But we have a very nice theorem, very useful. If it happens that x and y are independent random variables, then covariance of x and y is 0. So for independent ones, covariance, guys, will relate to correlation, by the way, right? So if they are not related to one another, if one does not influence the outcomes of the other, then the covariance will be 0. Let's see why. Okay, guys, so covariance is made out of 2 parts. It's the expected value of x and y, and it's the expected value of x times the expected value of y. So you can obviously see this will be 0 whenever the expected value of x times y is the product of expected values. You agree? If I can show that expected value xy is expected value x times expected value y, then that's 0. Are you with me? Now let's see what happens there, guys. So what is the expected value of x and y? It is every combination of x against every combination of y times the probability. Sometimes this probability is 0. Right? So I mean, one way to calculate the expected value of x and y is simply to add up. So we know all the scores for x and we know all the scores for y. And we can calculate the probability that x and y meet. Yes? So those are the labels of x, and those are the labels of y. Right? When do they meet? So that is equal if we have independence, guys. It's not always true, right? This is then the same thing as the probability of x equal to xi and y and times probability of y equal to yj. Do you see what I can take this probability and I can break it apart. And then I can group the xi's with the probability and the yj's with their probability. And what does it say now? Now, in this form, guys, with independence, it says that we have every combination of x and with the probability times every combination of y with the corresponding probability. And that's the same as multiplication. That's what happens when you FOIL things, right? So it's additional. That's when you expand one parenthesis multiplied by another. That's when one thing combines against another. Yes? Do you see what happens then? And that then you can factor it out. You see, I can factor it out, and that now becomes the expected value of x. That now becomes the expected value of y. So if we have independence, if this can be broken into probability of x equal to xi and y equal to yj, then I can multiply the probabilities. Do you need an example of that, or some sort of thing that I need to draw for you to get this idea? Or are you good? Let me know quickly. So you understand, guys, what we did here. We factored out. Essentially, we factored into 2 parentheses, because what did I realize? It's a very important thing to realize. Like in this form, I cannot separate the x's from the y's. Yes. You see, what we're dealing with is a very simple idea. It's one parenthesis against another, and if you multiply it out, then you will see every term from this parenthesis against every term from this parenthesis. Now, in this form, it's still not clear, you see, because I do not know which combinations of xi and yj can actually have non-zero probability. But in here, it's clear that that it's so, right? You see, if basically we have each xi is assumed with non-zero probability. In other words, xi is possible and xij is possible, but maybe they never meet. Maybe if this probability is 0, then they don't meet. There is no xi times xj. But if we have independent random variables, they will always meet. There is always xi times xj. And you can see that here. And then I can unfold. Yes? And then I have this product times this product. That's the expected value of x, expected value of y. And then last calling, guys, do you want me to draw you an example of where they meet, where there's something like that, right? Last call. Okay, nobody wants it. Everybody understands it so perfectly. I'm glad. Yes, please, example. Okay. It's just a simple example. Okay, guys, I will show you what can happen when they, when I mean meet and not meet. Okay, so imagine we have a simple sample space. Let's say we have outcomes 1, 2, and 3, right? So that's my sample space. And let's assume each of them with probability, each of them has probability P, yes? Each 1/3 is the probability of each outcome, yes? So then what we have is, let's suppose that we have that 1 and 2 are mapped to the value, let's say they're mapped to the value 10, each of them, right? 10. And this, no, sorry. And this is mapped to the value of 5. Good. And this is the action of x with the corresponding probability. So that's the relabeling of x. So I relabeled the 10, 10, and 5. Now let's consider the action of y. So imagine that the action of y is labeling this as maybe -1, this as -1 again, and this as 2. Yes, this as 2, and that's the action of y. So far clear, right? We have x and y, and they're just acting on the same space. Yes. Now, what is the expected value of x multiplied by y? Yes, x multiplied by y. I can consider which outcomes match, right? So I can do that. Easiest way to do that is to just actually group by the sample space, right? Because then I will not miss anything, right? So the expected value of y is what? It's look at it, x times y, right? So if the outcome is, so it's going to be x of 1, y of 1 times 1/3 plus x2 y2 times 1/3 plus x3 y3 times 1/3. You agree? And that's what this product means. And what is this? What is x1 times y1? x1 times y1 is 10 times 2, right? So it's 10 times 2 times 1/3 plus x2 times y2 is 10 times -1 times 1/3 plus the last one, x3 times y3 is just 5 times -1 times 1/3. Yes. You can do it in many orders, but my point is you can look at the summation and tell me, are X and Y, by just looking at it, are X and Y independent? Are X and Y independent? Well, let's see. Right, what are the combinations here? Right, we have how many combinations? We have 2, -1, 2 and -1, and here we have 10 and 5. Right, so does 10 meet 2? 10 meets 2, but 5, you see, 5 never meets 2, for instance. Right, 5, you don't see it next to 2. You see, we have 10 meets -1. 10 meets 2, but 5 and 2 don't ever meet. And if they were independent, they would have met. You understand? They would have, if it were like a product, they would have met. So they are not independent, they are dependent. You see why I mean, even without, I mean, I could have done it in so many ways, but based on that calculation we did before, it was clear that this calculation that we did here, it's clear that that they cannot be independent, because you see, look at 5. 5 meets against -1. Does 5 meet against 2? We don't ever see 5 meeting against 2. Right? If they were independent, we would have seen 2 times 2. We would have seen 4 terms here in summation. That's for sure. You see? So so this is not the expected value of X times the expected value of Y. What would that be, guys? Right? If I calculate the expected of X times the expected of Y, that would be each of those times 1/3 times each of those, which means they meet. You agree? Are you following? I hope the example is sufficient for you to understand what I mean by this multiplication thing. Right? I hope I don't need to write it. You see, so the expected value of X times the expected value of Y is what? Expected value of X is just 10 times a third plus 10 times a third times 5 times a third, multiplied by the expected value of Y, which is 2 times 1/3 minus 1 times a third minus 1 times a third. And when you multiply them out, you should have seen everyone meeting everyone else. Yes. Very good. So this is a crucial calculation, guys. So make sure you truly understand it. You see what the key is here. Look at it. I can separate. It's every X against every Y. But sometimes the probability here is 0. You see, probability X equal to Xi and Y equals Yj is 0. If it's 0, then they don't meet. But if we have independence, then this probability is probability X equal to Xi times probability Y equals Yj. And that probability is not 0. Do you agree? I mean, assuming we're listing only the X's that have non-zero probability of appearing and all the Y's that have non-zero probability of appearing. Then this is not 0, this is not 0, then they met. Each X met against each Y. Right? As you saw in that other example, 5 did not meet, I believe, 2. Which means the probability that we have X equal to 5 and Y is equal to 2 is 0, because they will never, it never happens because you don't pick the same outcome. You understand, guys? Right, X and Y are just those labels, and what you're picking is a sample space. I hope you see how random variables work there, right? Right, so what you actually pick when you say X times Y, you're just picking the sample space and you're just comparing the labels of the outcomes in the sample space. Right, so 5 never matches 2 because there is no outcome that is labeled in red as 5 and in green as 2, which means the probability of 5 meeting 2 is 0. but when each can meet against everyone else, the variance is the variance of the sum is the sum of the variances. Okay, and that's because the covariance is 0. Each of those will be 0. Right? If they're independent, then each of them are 0. If X is independent from Y, if X is independent of Z, if all of them are independent, then the covariance is 0 because the expected value of X times Y is expected value X, expected value Y. When you subtract the product, that's it. Good. All right, guys. So for today, it's enough, and very soon we will use that to calculate different variances for non-independent random variables as well. So make sure you do understand it. And make sure that it's very picturesque what you see when you look at those variables. All right. Have a good evening, guys. Take care.